Okay, hi guys. Thank you very much for all the people who submitted feedback based on Module 5. I'm just going to quickly whiz through it really and then see what we can tailor to kind of cover the areas perhaps you're less confident on. I had 14 responses, which is a wee bit on the low side. So if you haven't yet responded and you want to do so, or you want to just email me anything you don't get, just please do so. Because the more you tell me, the better it is. And I think this way is probably better than getting you to an end of module test. However, if you do want to do an end of module test, please give me a shout. I'll happily ping it over to you and I'll mark anything you do. But I think you're at home. I don't think making you do a test is particularly beneficial. So let's have a quick whiz through. Right, so whiz through the first things. Right, formulations you're pretty happy with. Most people seem okay with it. These definitions, they're just quick learning things. So hopefully nothing too nasty there. Right, chromatography. We did do chromatography and we did do RF values just, so I think most people are okay with that. I think chromatography itself is pretty straightforward. Calculating RF, again, learning an equation, which is a bit more complicated, but I think pretty confident. Right, melting point purity, little bit of a sort of spread there. Very simply, everything has a melting point. So if it's pure, it'll have a fixed definite number as a melting point. It won't be a range of numbers. And the closer to the proper number your sample is, the purer it is. So if it should be 120 degrees and you're getting 118 to 19, that's sort of fairly pure. If it should be 120 degrees and it's 124 to 128, that's not pure. A, it's higher and it can never be higher. B, if it's a range, that's not good either. Okay, gas tests, seem pretty happy with gas tests, so that's quite good news. There's 4 of them, so I'm happy that you're good with those. We'll come back to them later actually. We will look at them in Module 7 again, so a bit of revision for you then. Flame tests we're all really good with, so that's pretty good. Right, flame emission spectroscopy. This is an area that people are much less happy with. So really, very, very basic level. What is flame emission spectroscopy? It's a machine that does a flame test for you. So what do? You bang your sample in, the sample gets vaporized, so it gets burned. But the colour that comes off it, the flame colour that comes off it, is then split into a spectrum. So imagine shining light through a prism like the Pink Floyd album cover and you get a nice rainbow. Where there are gaps in that rainbow, that is a spectrum. That equates to electrons in shells jumping up and down between energy levels. Right, so you get a spectrum. And that spectrum will be unique. It's like a fingerprint. So what you do is you get the fingerprint spectrum that you've got, and you've got your big book of other fingerprint spectrums. You just compare the lines. So don't worry too much about it. It's very much an analytical technique, and I'll make sure I do ping something out there to help with this. Okay, guys, it's obviously an area you're keen on. Right, precipitation tests. Again, this is this point really where lockdown sort of kicked in, so we were right at the cusp of doing this practically. We did do it very briefly, but I think people are struggling with this a bit. But what is the test? The test is you've got your unknown metal ion. What ion is it? Is it copper? Is it iron 2? Is it iron 3? Is it calcium ions? Is it magnesium ions? Is it aluminium ions? And what you do is you've got these colourless solutions. You add to it colourless solution of sodium hydroxide. What happens is the metal ion bonds with the hydroxide ion and it forms an insoluble precipitate. Precipitate is a solid formed from the reaction of two liquids, two ions. And the colour of the precipitate tells you what it is. So you should know blue, green and orange. If it is orange, it's iron 3. If it's green, it's iron 2. If it's blue, it's copper. Anything else will give you a white precipitate. So white precipitates calcium, aluminium and magnesium. Those are the 3, and you can use flame test to identify those, or if you add an excess, aluminium will be dissolved. So there's a clue there as well. Okay, so it's worth revising this. It will come up. these required practicals we will come back to leading up to the exam in Year 11, assuming that the exams follow what the sort of the way they have in the past. We just don't know that because we don't know how we're all going to respond in education to your having to learn from home for a significant period of time. So don't worry about that. These things will get sorted out later, as they have done for this year's Year 11 and this year's Year 13. No one's been left high and dry. So, all being well, we will look at these required practicals in Year 11 because a lot of marks riding on them, so we will revise this. Okay, but this is another area to have a quick look at. Carbonate ions, again, a bit weak on this one. Why? Because it's a required practical and we kind of rushed it because we were out the door. So, what's the test for a carbonate ion? Well, this is a really easy one actually. Carbonates are bases, they react with acid, and they fizz because they make carbon dioxide. So you can see the fizzing and you can test carbon dioxide, which you already have told me you're confident at. This is something we will come back to later. We'll look at acids and bases later on, so I'm not too worried about this for the time being. I will make a point of it. Right, colour and test of halide testing. So what are the three halides? You've got chloride, bromide, iodide. Right, there is also fluoride, but we're ignoring that. And what you do, these are colourless solutions. How do we identify what those colourless solutions are? What you do is you add to it silver nitrate. Now it needs to be acidified, so you need nitric acid and silver nitrate. That's the test. What happens? You get precipitates, you get solids formed. The colours: chloride, white; bromide, cream; iodide, yellow. Okay, test and results. So people who aren't sure on that, again, we did this practically. It's one of the last things we actually managed to do in school. It's worth learning it. Okay. Right, sulfate ions. We did the sulfate test on the same day. So again, we've got this sort of mixture of people who are sort of relatively confident, people who aren't. Okay, so test for sulfate is need barium ions. Barium chloride or barium nitrate will do. The specification I think says barium chloride, but it doesn't really matter. So barium chloride and hydrochloric acid. You need the acid in there as well. And what will happen is that will react to make barium sulfate, and you get a white precipitate. Okay, so just chuck in barium ions of whichever type, and you get a white precipitate of barium sulfate. Drinking water. All right, we're making it potable. How do you make water drinkable? Water treatment. That seems to be a fairly good thing. So excellent, well done. Desalination by two methods. Desalination. D means removal of. Sal is salt. How do we get salt out of water? There's two different methods. Right. There was a video we looked at, and there was a sort of required practical we talked about. Method number one: evaporation. So you evaporate the water off, and you then recondense that. That's called distillation. You use a still, and the salt gets left behind. Water evaporates. Water vapour goes up the tube. It then passes down a condenser. The condenser then turns it back to a liquid. You get pure water at the end. Method one. Method two is you use a process called reverse osmosis. Now, at a very simple level, think of it a little bit like you've got salt water at one end, you've got a very fine filter, and you force water through. Salt molecules can't get through, or salt ions can't get through, but the water can. So it's called reverse osmosis, and that's the other method. Both of those methods are daftly expensive because they use huge amounts of energy. We don't need them. Why? Because, like today, water falls out of the sky in this country, so we're okay for that. But in countries that are oil-rich, generally have lots of money available for energy, they can use that. Okay, so if you've got the combination of loads of money in terms of energy because you've got lots of oil, and you've got a problem with drinking water because you are in a desert, then these are the sort of countries that would use desalination plants, either by distillation or more likely by reverse osmosis. And if you go back to the lesson where we did that, I did ping up a little video on that. We showed the process. Well worth having a look at if you're not 100% sure. Okay, moving on. Wastewater treatment, seemed fairly okay with that. You did a poster flowchart on that. how we treat wastewater, sewage plants and all the rest of it. So I'm pretty pleased with how confident most people are there. So that's excellent. Finite renewable, pretty good with that. Phytomining and bioleaching. Right. What is phytomining? What is bioleaching? The key thing about this is about getting copper. Copper ore now is pretty low quality because we've dug out all the good stuff we could find and we've been doing it for about 100 years. So it's getting low grade copper ores and getting the copper out. Bioleaching, bio means it's got living stuff in it, and the way that works is you use bacteria, and the bacteria then effectively absorb the copper, and then that extracts it from there. So that's using bacteria. Phytomining is where plants absorb it through the roots. So you use plants, they absorb the copper ions through the roots, the plant's taken away, the plant is burned, the copper is extracted from the ash. Right, so those are the two different methods. So bio, because that's got the one bacteria. Phytomining, that's the one where you're growing stuff and you're extracting it from plants. Okay, life cycle assessments. We're pretty good with that, which I'm really pleased by because everyone hates life cycle assessments. I think the fact you've done loads of questions on that really has demystified the process, made it a lot more straightforward. And the people who've done that and have submitted those, well done, you've done a great job on those. Okay, glass and metal recycling, pretty straightforward, I think, for most people there, so that's excellent. For alloys, the elements they contain, I think we're mostly okay with that. Corrosion, we were pretty good with that as well, and we'll come back to that. Right, it's worth pointing out, we'll come back to that. Thermo-softening, thermosetting, I think most of us are okay with. It's all to do with the cross-links. Okay, weak cross-links, intermolecular forces, it's a very soft plastic, it can be melted and reformed. Thermosetting has hard, rigid bonds between them, usually covalent bonds, and that means it cannot weaken until you break all the bonds. That's the point where you char it or burn it. Okay, we'll come on to polymers again next year, so we'll come back to this, don't worry too much. Composite materials, bit of a mixed bag there. If you can't remember the orphans, the kittens and the crocodile. Okay, composite material, reinforced concrete. What is glass made from? Bit of a mixed bag there on glass. So what is it mainly? It's mainly silicon dioxide because it's sand mixed with other things. So with borosilicate, it's got boron in it. So have a quick look at the PowerPoint if you don't know. I wouldn't worry too much about it. Okay, the main thing is it's got silicon dioxide in it. Harbour process, you were all over that. I'm not surprised, it's your second time of meeting it, but you were good, which is excellent. Le Chatelier's principle. Oh, I was so pleased with this. You did a cracking job on this one, by and large, in the last assessment. So I'm really, really pleased you've learnt that. So well done, because this is the hard stuff. Okay, NPK, yeah, pretty happy with that. Look on the periodic table. N, nitrogen. P is phosphorus, oddly, and K, potassium. So if you're not sure, look on the periodic table. Right, acids and bases and fertilizers and stuff. Right, this is the weak bit. And the reason why it is because we haven't done it yet. We haven't done acids and bases. So when we come back to it, can I also apologise for the fact that I've misspelled fertilizers. But when we come back to it next year, we'll look at acid and base theory from the very, very start. We'll look at acid and base reactions, neutralizations. We'll look at it practically. We'll look at all of those equations and how we then make salts and how we name salts. Fertilizers are just salts. So I'm not actually going to do anything more on this at the moment because we'll come back to it next year. If you're not 100% with it right now, that's absolutely fine. Okay, so that's everything, guys. I'm going to ping out a couple of little resources for the things that you're not so sure on. I think this has been quite useful for me, so thank you very much for those people who did submit it. If at the end of all this you still don't get it and you want to come and have a chat, just ping me at my usual email address and we'll see how we go from there. But otherwise, guys, you take care and I'll see you soon.